Hi everyone, welcome to another video which is hybridization. In this video we are going to discuss about the definition of hybridization, then the need of hybridization, why do a molecule undergo hybridization, then mechanism in the sense how hybridization occurs, then different types of hybridization undergone by different molecules, the central atoms of different molecules, then examples of each of these types of hybridization. So we are covering all these things in today's video. So first of all, let's see what is meant by hybridization. Hybridization is the process of intermixing of atomic orbitals of slightly different energies to form new orbitals of equivalent energies and identical shape. So let's see what is meant by these terms. So when we take any molecule, say for example methane, during the formation of this molecule, we know carbon is the central atom. So the central atom combines with 4 hydrogen atoms to form a methane molecule. And first of all, we should know the configuration, valence configuration of the central atom, that is 2s2, 2p2. It is having 4 electrons in the valence shell, and we know in order to combine with 4 hydrogen atom, this carbon atom should make available 4 half-filled atomic orbital, that is the formation of a covalent bond. We know a covalent bond is formed by the mixing or by the combination of half-filled atomic orbitals of the combining atoms. So here we know carbon has 4 electrons and the 2s electrons are paired, and the 2p electron, in 2p we have 2 electron. So in order to combine with or in order to bond with 4 hydrogen atom, first of all this should make available 4 half-filled orbital. So what happens is the ground state configuration of carbon, there occurs a rearrangement. That means the 2s electron, one of the 2s electron in the paired configuration will be promoted to the 2p, vacant 2p orbital, thereby make available 4 half-filled atomic orbitals. So this is the first step. So now the carbon has got 4 half-filled atomic orbitals, and in this case it cannot directly combine with 4 hydrogen atom, because we know the hydrogen atom, each hydrogen atom is having a configuration of 1s1. Okay, so this 1s electron, when it is approaching the carbon, central element carbon, the 4 atomic orbitals are of different types. That is, one is a 2s atomic orbital, the other 3 are 2p atomic orbital. So their energy, shape, etc. are different. When we compare the 2s and 2p, their energy and shape are different. So the incoming hydrogen atoms see a difference in the type of atomic orbital. So it cannot combine with the hydrogen atoms as such. So before combining or before bonding with the 4 hydrogen atom, the carbon should undergo a mixing process. Okay, this carbon atom having the excited state configuration 2s1, 2p3 undergo a mixing, an intermixing process. That means 4 of these atomic orbitals mix together to form 4 new orbitals, and these 4 orbitals are called Sp3 hybrid orbitals. We can call them as 4 Sp3 hybrid orbitals. Now all these 4 hybrid orbitals are having same energy and same shape. So they will arrange across the carbon atom in a tetrahedral manner. Okay, so the carbon atom having 4 atomic orbitals. Now these are called hybrid orbitals because these 4 atomic orbitals mix together to form 4 hybrid orbitals or 4 new orbitals, and all these 4 orbitals are having same energy and same shape. So they arrange around this central carbon atom in a tetrahedral manner in order to minimize repulsion, or in order to have maximum stability or minimum repulsion, they arrange across carbon atom in a tetrahedral manner. And now the 4 hydrogen atom, the incoming hydrogen atoms has equal preference to all the 4 hybrid orbital, because all are of same energy and same shape. So what happens now? The hydrogen atoms with 1s1 configuration overlap with the half-filled hybrid orbitals of carbon to form a tetrahedral methane molecule. So this is the process of hybridization. That means the intermixing of atomic orbitals of slightly different energies to form new orbitals having equivalent energy and identical shape. And this is the definition of hybridization. So atomic orbital mix to form new hybrid orbitals. And we know the need of a hybridization is to attain same energy and same shape orbitals. The atomic orbitals, the slightly different energy atomic orbitals combine to give hybrid orbitals of same energy and same shape. Okay, so this is the definition of hybridization, definition and also the need of hybridization. Now let's see in detail about different types of hybridization. Now let's take Sp hybridisation. In order to explain Sp hybridisation, we can take the typical example of beryllium chloride molecule. So beryllium chloride I have chosen because we know in Sp hybridisation there are 2 hybrid orbitals. So we should select a central element having 2 having 2 bond pairs, or it is bonded to 2 other atoms. So the ideal selection would be a second group element. So that is why I selected beryllium chloride, and for beryllium atom the ground state configuration is 2s2, 2p0. And in order to combine with 2 chlorine atoms, the beryllium atom should make available 2 half-filled atomic orbitals. So what happens? One of the 2s electron get promoted to the 2p subshell. So the excited state configuration become 2s1, 2p1, 2s1 and 2p1. Now there are 2 half-filled atomic orbitals, so these can combine, or these 2 will mix together because they are having different energy and different shape. We know s orbital is spherical in shape, p orbital is dumbbell in shape, and their energies are also slightly different. So now these 2 atomic orbital undergo intermixing to form 2 new hybrid orbitals, which are called Sp hybrid orbitals. They are having, both these hybrid orbitals are having same energy and same shape, and the 2 hybrid orbitals are arranged around the beryllium atom in such a way that they have minimum repulsion, because both the hybrid orbitals has electron. So in order to reduce repulsion, the 2 hybrid orbitals arrange in a linear fashion, in a linear manner at a bond angle of 180 degree apart. Now the hybridization is ready, hybridization is over. Now the 2 chlorine atoms, each having a valence configuration 3pz1. We know chlorine atom is having the valence configuration 3s2, 3p5. So 3p5, in the 3p5 we have 3px2, 3py2 and 3pz1. Only the 3pz orbital is half filled, all others are paired. So the 3pz orbital having 1 electron combine or overlap with the hybrid orbitals of beryllium to form a beryllium chloride molecule having linear geometry and 180 degree bond angle. So this is the Sp hybridization, where we have taken the example beryllium chloride. Beryllium is having a ground state configuration, valence configuration 2s2 in the ground state, and one of the 2s electron get excited to 2p level in order to make available 2 half-filled atomic orbitals. Now the 2 half-filled orbitals mix together to form 2 Sp hybrid orbitals. Both of them are having same energy and same shape. So these two arrange around the beryllium atom in a linear fashion to reduce the repulsion between the electrons. And the two chlorine atoms with 3p-Z configuration, 3p-Z1 configuration overlap with the hybrid orbitals of beryllium to form a beryllium chloride molecule whose geometry is linear and the bond angle is 180 degree. So this is the hybridization of beryllium chloride or explanation for Sp hybridization. Next we can discuss Sp2 hybridization. So for discussing Sp2 hybridization, we know there are three hybrid orbitals. So a central element with 3 valence electron would be the ideal choice. So we can take a 13th group element, for example BF3, boron trifluoride. So for boron trifluoride, we know the boron atom, the ground state configuration is, valence configuration is 2s2 2p1. It has 3 electrons in the valence shell. And we know in order to combine with 3 fluorine atom, it should make available 3 half-filled atomic orbitals. So for that, one of the 2s electron get promoted to the 2p, and in the excited state the configuration become 2s1 2p2. Now this 1 2s orbital and 2 2p orbital mix together, or they undergo hybridization. Then that hybridization is called Sp2 hybridization. Okay, so the Sp2 hybridization involving 1s orbital and 2 p orbitals. So that is why it is called Sp2 hybridization, and resulting we get 3 Sp2 hybridized orbitals. So since we have 3 orbitals, they will arrange around the boron atom to have minimum energy, and the possible method, the best possible method is to arrange in a trigonal planar manner so that they can have minimum repulsion. Okay, so the boron, this hybrid orbital, the 3 Sp2 hybrid orbitals arrange across or arrange around the boron atom in a trigonal planar manner to have minimum repulsion among the electrons. So now the hybridization is ready. Now the boron, the fluorine atom, each fluorine atom with 2p-Z1 configuration overlap with the half-filled hybrid orbitals of boron to form BF3 molecule. So we will get a BF3 molecule with the geometry trigonal planar. BF3 is having a geometry trigonal planar with bond angle 120 degree. Each bond angle will be 120 degree. So this is the Sp2 hybridization, and the typical example is BF3 molecule. Now let's explain Sp3 hybridisation. For Sp3 hybridisation, let's take typical example of methane molecule. We know for Sp3 hybridisation there are 4 hybrid orbitals. So we should take a central element with 4 valence electron. That would be the ideal selection. And for carbon atom, we know the ground state configuration is 2s2 2p2. That is, we have 2s2 2p2. This is the ground state, and in order to make available 4 half-filled atomic orbitals for combining with 4 hydrogen atom, this should make available 4 half-filled atomic orbitals. So this will be promoted, one of the 2s electron will be promoted to the 2p subshell, and the excited state configuration become 2s1 2p3. Now 4 half-filled orbitals are ready. Now these 4 half-filled orbitals undergo mixing to form 4 Sp3 hybrid orbitals. So new 4 hybrid orbitals having same energy and same shape are formed, and these 4 hybrid orbitals arrange around carbon atom in a tetrahedral manner to have minimum repulsion between them. Okay, so this will have a tetrahedral arrangement, and now 4 hydrogen atom with 1s1 configuration can overlap with the 4 hybrid orbitals of carbon atom to form a methane molecule, tetrahedral methane molecule. Tetrahedral methane molecule with bond angle 109.5 degree. So this is the Sp3 hybridization. We have taken methane as the example, and for carbon there is a valence configuration to S22P2. In order to combine with 4 hydrogen atom, it should make available 4 half-filled orbitals. So for this, one of the s electron get promoted to 2p level, and the newly formed the 4 half-filled atomic orbitals 1s and 3p, they will combine or they mix together to form 4 sp3 hybrid orbitals, and these 4 sp3 hybrid orbitals are oriented along the corners of a tetrahedron at a bond angle of 109 degree 28 minutes, or let's say 109.5 degree. So now each of the hybrid orbital now undergo overlapping with each hydrogen atom with 1s1 configuration to form a tetrahedral methane molecule with bond angle 109.5 degree. So this is the sp3 hybridization. Next, let's take Sp3D Hybridisation. So Sp3D means now we got one d orbital also involved. The total number of orbitals would be 5, 1s, 3p and 1d. So an ideal example for this is a central element having 5 valence electrons. So it would be a 15th group element. 15th group element would be ideal. That is nitrogen family. So we can take phosphorus. Nitrogen we cannot take because it doesn't have d orbitals. So we can take PCl5 as the example for this Sp3D hybridization. And for phosphorus, we know the valence configuration is 3s2 3p3, 3s2 3p3 and 3d0. So we can write 3s2 3p3 3d0. In order to combine with 5 fluorine atom, this phosphorus should make available 5 half-filled atomic orbitals, but here only 3 are there. So one of the s electron get promoted to the d, and the excited state configuration will be 3s1 3p3 and 3d1. So these 5 orbitals 1s, 3p and 1d orbitals undergo mixing or hybridization to form 5 sp3d hybrid orbitals. So newly formed hybrid orbitals, there are 5 in number because 5 atomic orbitals are combining. So these 5 orbitals, in order to reduce repulsion or in order to have maximum stability, they arrange in a trigonal bipyramidal manner around the central element phosphorus. So we have phosphorus, so this is the trigonal plane, and bipyramidal, that means 2 bonds. 3 hybrid orbitals are in the triangular plane and 2 hybrid orbitals are above and below the triangular plane. So now the remaining, we know 5 chlorine atoms with 3pz1 configuration, valence 3pz1 configuration overlap with the 5 hybrid orbitals of phosphorus to form a PCl5 molecule. a trigonal bipyramidal PCl5 molecule. So we can show the geometry as a trigonal bipyramidal molecule. So it is having two bond angles. The equatorial bond angles are 120 degree and axial bond angle 90 degree. So this is Sp3D hybridization. For Sp3D hybridization, we have taken the PCl5 molecule as typical example, and the valence configuration of phosphorus is 3s2, 3p3 and 3d0, and during excitation one of the s electron get promoted to the 3d subshell, and these 5 orbital 1s, 3p and 1d orbitals mix together to form 5 Sp3D hybrid orbitals, and these 5 orbitals are arranged in a trigonal bipyramidal manner around the phosphorus atom in order to have minimum repulsion. Now each of the chlorine atom with 3pz configuration, 3pz1 configuration overlap with the half-filled hybrid orbitals of phosphorus atom to form a PCl5 molecule having trigonal bipyramidal geometry and two bond angles. The equatorial bond angles 120 degree and axial bond angles 90 degree. So this is the Sp3D hybridization. Next, in the same way we can discuss Sp3D2 hybridization. So for Sp3D2 hybridization, we know there are 6 hybrid orbital. So an ideal example we can take where the central element is having 6 valence electron, that is 16th group element. So let's take SF6 molecule. Sulfur atom, we know the ground state configuration is 3s2, 3p4 and 3d0. This is the ground state configuration, and in order to combine with 6 fluorine atom, it should make available 6 half-filled orbital. Only 2 are there. So what happened? The 2 electrons, that is one of the 3p electron get excited to 3d and also the 3s electron get excited. So the excited state configuration become 3s1, 3p3 and 3d2. So now these 6 orbitals 1s, 3p and 2d, so total 6 atomic orbitals intermix to form 6 Sp3D2 hybrid orbitals, and these 6 hybrid orbitals are arranged around the sulfur atom to have minimum energy, and that possible, the best possible arrangement is octahedral arrangement. So there will be an octahedral arrangement of octahedral arrangement of hybrid orbitals. Each hybrid orbital has 1 electron, and now 6 fluorine atom with 2pz1 configuration overlap with the half-filled hybrid orbitals to form an octahedral SF6 molecule. Okay, so we'll get one sulfur atom connected to 6 fluorine atom to form an octahedral molecule with bond angle 90 degree. So this is the geometry of SF6 octahedral geometry and Sp3D2 hybridization with bond angle 90 degree. So this is all about Sp3D2 hybridization. Next, let's take Sp3D3 hybridisation. So for Sp3D3 hybridisation, we know there are 7 hybrid orbitals. So we should take an ideal example where the central element is having 7 valence electron. So we can take a halogen compound and let's say IF7, an interhalogen compound. So where iodine is the central element, and for iodine the ground state configuration is 5s2, 5p5 and 5d0. This is the ground state configuration. In order to combine with 7 fluorine atoms, it should make available 7 half-filled orbitals. So all the 3 paired electrons get promoted to the 5d orbitals, and the excited state configuration become 5s1, 5p3 and 5d3. So these 7 atomic orbitals undergo mixing or hybridization to form 7 Sp3D3 hybrid orbitals, and these 7 orbitals are oriented in a pentagonal bipyramidal manner around the central iodine atom. Okay, so there will be a pentagonal bipyramidal arrangement of hybrid orbitals. Now each of these hybrid orbitals get overlapped with the 2p-Z orbital of 7 fluorine atoms, and thereby we get IF7 molecule with pentagonal bipyramidal geometry. So this is the geometry for IF7, a pentagonal bipyramidal geometry. So that is about Sp3D3 hybridization. We have taken an interhalogen compound IF7 as the typical example. It is having 5 bond pairs alone, 7 bond pairs. Central atom iodine makes available 7 half-filled atomic orbitals, and these will mix together to form 7 hybrid orbitals, and these 7 hybrid orbitals are oriented in a pentagonal bipyramidal manner to form IF7 molecule. So this is Sp3D3 hybridization. Hence we have completed these different hybridization like Sp, Sp2, Sp3, Sp3D, Sp3D2 and Sp3D3. So these are the hybridizations where we have only bond pairs. Okay, so let's compile it in this way. We have Sp hybridization, example beryllium chloride and geometry linear with a bond angle 180 degree, and Sp2 hybridization, typical example BF3, trigonal planar geometry. Sp3 hybridization, example methane, tetrahedral geometry, and for Sp3D we have 5 orbitals, so PCl5 as the example, and its geometry will be trigonal bipyramidal. And when we have 6 hybrid orbital, that is Sp3D2 hybridization, and a typical example we can take SF6 molecule with octahedral geometry. And finally Sp3D3 hybridization, example we can take IF7. There are 7 hybrid orbitals, so we have a pentagonal bipyramidal geometry. So these are the hybridization and geometry of molecules containing only bond pairs. So in these cases we can see in all the cases we have only bond pairs, no lone pair. So in the next video we can discuss about hybridization of molecules having lone pairs also, that is the VSEPR theory concept. Okay, hope you all understood all these. Thank you all. Thank you for watching.